Okay. In the first section, the last speakers is Mücahit MERAL. He's a PhD student and he's from the Yozgat Bozok University in Yozgat. The title of his presentation, Semi-Free Hamiltonian Circle Actions on 8-dimensional symplectic manifolds. If you are ready, Mücahit, you can share your screen or your presentation.
Okay. First of all, I would like to thank the committee for inviting me to this workshop. I would also like to thank the participants. Okay, let's start. Firstly, I want to mention the historical background of the problem. Problem is that simply, what is the relation between Hamiltonian action and fixed points? The first result is Frankel's theorem. In 1959, Frankel proved that the symplectic S1 action is Hamiltonian if and only if it has fixed points for the Kahler category. Then Ono extended to this result to symplectic category. Ono proved that the symplectic S1 action is Hamiltonian if and only if MW is symplectic and satisfies the Lefschetz condition in 1988. After this, McDuff proved that the Frankel's theorem is true for 4-dimensional symplectic manifold. This means that the symplectic S1 action is Hamiltonian if and only if it has fixed points for 4-dimensional symplectic manifold. Then she gave a counterexample for 4-dimensional symplectic manifold. She showed that there is a 6-dimensional manifold with a symplectic non-Hamiltonian S1 action whose fixed point set is non-empty. Then many people try to find some condition on the manifold M which make a symplectic circle action is Hamiltonian. Tolman and Weissman, Godinho, Lupton, Oprea proved Frankel theorem under some other conditions. Tolman construct a different example. Her example is different from McDuff's example because in Tolman's example, all fixed points are isolated. Therefore, Tolman's example is extend to symplectic category, extend to even dimensional symplectic manifold. As McDuff and Tolman showed, the existence of fixed points does not guarantee that symplectic circle action is Hamiltonian. Chu, Huang, and Su discovered a condition on the 6-dimensional symplectic manifold. In this talk, we will discuss Chu, Huang, and Su theorem, and if time permits, I will talk about our work on 8-dimensional symplectic manifold. Okay, I want to give some main definition and theorems. Firstly, I want to give the definition of symplectic manifold. Let M 2n-dimensional be a smooth manifold. A 2-form W on M is called symplectic if it's called closed and non-degenerate. We call the pair MW as a symplectic manifold. As for the definition of symplectic S1 action, an S1 action on MW is called symplectic if it preserves the symplectic form W. Okay, let's go on. If the contraction of W with respect to X is exact, then we can say the action is Hamiltonian. So we know that if the action is Hamiltonian, then there exists a function h from M to R such that EXW is equal to DH, where H is called a moment map of the action. Okay, these conditions are equivalent. This means that if EXW, the contraction of W with respect to X is exact, if and only if there exists a function H such that EXW is equal to BH, if and only if action is Hamiltonian. Okay, I want to give two examples for Hamiltonian action and non-Hamiltonian action. Consider the two-sphere. The standard symplectic form on two-sphere is W. W is equal to dz exterior product d theta, and vector field X is del over del theta. As in figure, we have a map Z from two-sphere to R. You can consider this map is weight height map, or you can consider this is the projection map, two-third component. Theta can be considered relation, rotation. X can be considered rotation. Okay, we observe that S2 has two fixed points with respect to map Z, which are south and north pole. So X is the vector for X is Hamiltonian by using Frank's theorem. Okay, we have another example, non-Hamiltonian example. Consider the torus. Torus can be written as S1 cross product S1. There are two generators of S1 cross product S1, say theta 1 and theta 2. Let W, 2 from W, is equal to T theta 1 exterior product T theta 2. We have two vector fields which are x1 is equal to del over del theta 1 and x2 is equal to del over del theta 2. We have already W, x1 and x2, so we can evaluate the contraction of W with respect to x1 and x2. If we evaluate, we will obtain T theta 2 and T theta 1. We observe that they are close. EX1W and EX2W are close. So X1 and X2 symplectic vector field. Okay, consider the map theta from torus to R. This map is not well defined. Also, it has no fixed point. So X1 and X2 are not Hamiltonian. X1 and X2 are symplectic, but not Hamiltonian. Okay, now I want to give the definition of semi-free symplectic S1 action. The symplectic S1 action on MW is semi-free if it is free outside of fixed point set. This means that if the symplectic S1 action on M is semi-free, it is free on regular levels. M to the power of S1 is fixed point set here. Okay, symplectic symplectic reduction or reduced space is the main object for this. Assume that symplectic S1 action on MW is semi-free. Take semi-free symplectic S1 action. Let mu from M to S1 be a generalized moment map. Generalized moment map is a S1 value function, and generalized moment map holds many properties of moment map. Locally, they are same. Okay, take a regular value, t is in S1 of mu. We can evaluate the inverse image of t under mu. We observe that this manifold is a 2n minus 1 dimensional free S1 manifold. So mu inverse of t over S1 is a principal S1 bundle over mu inverse of t over S1. Since the action is semi-free, this means that the action is free on regular levels. So we can say that since the action is free on regular levels, phi inverse of t over S1 is a smooth manifold with the induced symplectic structure. It is called a reduced space of M or symplectic reduction of M. If we know that the dimension of M to M, mu inverse of t, the dimension of mu inverse of t is 2n minus 1, and the dimension of mu inverse t over S1, 2n minus 2 dimensional symplectic manifold, we will obtain a new symplectic manifold and denoted by M sub t Wt. I want to give an example for symplectic reduction. Consider the Cn complex numbers to the power of n. We have a standard symplectic form on C to the power of n. Say W. W can be written as polar coordinates as the sum of Ri, dri, exterior product, d theta y. Consider the S1 action, following S1 action on C to the n, S1x C to the n, map Ct phi from S1 times C to the n to C to the n. T is in S1 goes to phi t. Phi t is multiplication of e to the power et. Okay. Also, we have a vector field x as del over del theta 1 plus del over del theta 2 plus del over del theta n. So we have x, we have w, so we can evaluate exw, the contraction of w with respect to x. Exw should is equal to d mu. Okay, if we evaluate, we will obtain this term minus 1 over 2 d of the sum of ri squared. Okay, take the integral of both sides to obtain mu. Mu should be is this one minus module z square over 2 plus constant. If we choose the constant is equal to 1 over 2, I want to evaluate the inverse image of 0. So should this term should be 0, and then we will obtain model z is equal to 1. Z is in Cn, so model z is 1. So mu inverse, the set of mu inverse of 0 is equal to S2n minus 1. Okay, we should divide S1 mean was 0 over S1, S2n minus 1 over S1. This gives the Cpn minus 1, Cp to the power of n minus 1, complex projective plane, n minus 1 dimension. The real dimension of Cpn minus 1, 2n minus 2. So the symplectic reduction or reduced space of Cn is equal to 2n minus 2 dimensional symplectic manifold Cpn minus 1. Okay, I want to give the definition of the Stuttgart-Hackman function. F is a map from T star to R. T is a Lie algebra and T star is pullback of T. F is defined to be the symplectic volume F Kc is equal to W Kc, dimension of reduced space M Kc over 2 over M Kc. M Kc is the reduced space of M, and W Kc is induced symplectic form. W Kc is the symplectic form of the reduced space M Kc. Okay, dimension M Kc 2n minus 2 over 2n minus 1. So power should be n minus 1. Wn minus the integral of Wn minus 1 gives symplectic volume or the Stuttgart-Hackman function. The Stuttgart and Hackman prove that f is piecewise polynomial function and that it is a polynomial on any open region U consisting of regular values of the moment map phi. Okay, we will use this theorem on the proof of main theorem. This theorem is due to Lien. Okay, we will call this theorem as Lien's theorem. Assume that the action of a torus T on a connected closed symplectic manifold M is an effective Hamiltonian action of complexity 2 with moment map phi from M to T star, and assume that for any regular value Kc is in T star of phi, the symplectic reduced space M Kc has B2 plus is equal to 1, and the Stuttgart-Hackman function is log concave. Log concave means that its logarithm is concave. F is log concave. By definition, the logarithm of f is concave. Okay. Okay, let's go on. Another theorem we will use this one. This theorem is due to Guillemin, Lerman, and Sternberg. We will call this theorem as GLS theorem. Take a critical value C of the moment map and let epsilon is positive be such that the interval, the open interval C minus epsilon, C plus epsilon contains no other critical value of Kc. Okay, if F plus is the Stuttgart-Hackman function on the domain Cc plus epsilon. The domain of F plus is this one. The domain of F minus is this one. F plus and F minus are the parts of the Stuttgart-Hackman functions. We know that the Stuttgart-Hackman functions is a piecewise polynomial function. They are pieces of the Stuttgart-Hackman function. Okay, the jump of F can be evaluated this formula. We will call this formula as a jump formula. Volume Zi over dE minus 1 factorial, the product of Wij times T minus C dI minus 1. This sum is taken over all fixed components, fixed point Zi. Volume Zi is the symplectic volume of Zi, and dI is the half real codimension of Zi in M. And Wij are weights of the S1 representation on the normal bundle of fixed point Zi. And by definition, if Zi is a point, the symplectic volume of Zi should be 1. Okay, main theorem. As for the proof of main theorem, okay, let MW be a 6-dimensional closed symplectic S1 manifold with a generalized moment map mu from M to S1. Assume that the fixed point set is non-empty and dimension of each component at most 2. Then the action is Hamiltonian. If and only if B2 plus of reduced space is equal to 1 for any regular value Kc of mu. B2 plus, the definition of B2 plus, call that B2 plus of an oriented closed form manifold is defined to be the maximal dimension of the subspace of the second cohomology group on which the cup product is positive defined. Okay, Lin's theorem, you know Lin's theorem for the moment map, but we will use Lin's theorem in this theorem. We have, but we have also generalized moment map, but it's okay, no problem, because generalized moment map many holds many properties of moment map, and actually locally they are same. Log concavity, the property of log concavity is a local property, so in this case they are same. It's okay, we have not problem. Okay, the only part was put in this article, so we will focus the second part. It is enough to show that B2 plus of reduced space is 1 implies that the action is Hamiltonian. Okay, so assume that the action is non-Hamiltonian and assume that B2 plus 1. If B2 plus 1 by Lin's theorem, the Spartak function should be log concave on S1. Okay, but we know that every periodic concave function is constant, so f should be constant. So we must show that f is not constant to obtain a contradiction. Okay, we have two cases. In case 1, we have fixed point set contains fixed surfaces Z1, Z2, Zk, where C is in S1 is a critical value of phi. Okay, for these surfaces, the I can be evaluated following. Di, the half of codimension of Zi, the dimension of Zi 2. So codimension of Zi on M 4, the half of codimension of Zi 2. So for the fixed surfaces, Di is 2. Okay, we can write 2 in place of Di in this jump formula. Di minus 1 is 1, so power is 1. And this term is 1 factorial, which is 1. Okay, we will obtain this one. The jump of this two-dimensional function near C will be this one. Okay. The air index of all fixed surfaces zeta is 2. So the definition of index, what is the definition of index? Index of a fixed point defined as the twice numbers of negative weights. Most index, this is most index, the numbers of twice the numbers of number of negative weights. So if index of zeta is 2, we have one negative weight. Other weights are positive. So the product of Wij should be negative. One negative weight and all weights are positive. So the product of Wij for each fixed surfaces zeta is negative. So the sum of is negative. So the coefficient of t is negative. So this jump is non-constant. This means that f is non-constant. So we obtained a contradiction. Okay. Case 2. In case 2, we will focus the only fixed point set contains only isolated fixed points, Z1, Z2, Zk. For these points, di can be evaluated following. The dimension of zeta is 0. Codimension of zeta is 6. 6 over 2 is 3. Okay, di is 3. We can write 3 in place of di. Di minus 1 is equal to 2. So the power of 2 is 2 and 2 factorial. And if since zeta are points, volume of zeta is 1. We can write 1 in place of volume zeta. Okay. In this case, every index of zeta is 2 or 4. If index of zeta is 2, we have one negative weight. So the product of Wij is negative. If index of zeta is 4, we have two negative weights. So the product of Wij is positive. Then maybe the sum of 0, if the set Z1, Z2, Zk contains index 2 points and index 4 points simultaneously, then the coefficient of t squared may be 0. To solve this problem, we should make a blow up. After blow up, on one point, weights will change. If weights change, then the coefficient is not 0. Okay, I'm skipping some details because I don't have any time. Okay, after blow up, if he induces a generalized moment map, he had F induces a generalized moment map, F had. So by Lin's theorem, F hat should be constant. Okay. After blow up, in this section is this one. Induced symplectic structure is this one, and induced moment map is this one. Okay, and induced a jump of F hat this one, and the coefficient of T2 is non-zero. which contradicts that effect is a constant. Okay, I'm done.
Okay, thank you, Mücahit, for your nice talk and your nice presentation. Is there any comments or questions for Mücahit? I think it's okay. Okay, now we finished the first session of our workshop. The next section will be start 1 p.m. So we will have a half an hour break. See you at 1 o'clock.